Okay, welcome to this video for Chem 161, looking at some content for Chapter 4, where we'll be dealing with naming ionic compounds specifically containing transition metals. Okay, so naming compounds. These are ionic compounds, but they contain transition metals. So as you recall, the transition metals are found in the D block of the periodic table. Okay, so they're down here. What's unique about them is that based on their position in the periodic table, we cannot predict what charge value they want to have for their cations. They are still metals, of course. They are on the left-hand side of the staircase boundary here of the metalloids. They still want to lose electrons, they still want to form cations, but we cannot predict how many electrons they want to lose based on walking back towards the next lightest noble gas. That tool for us does not work. So for many ionic compounds that you might have to build or predict, you need to know the allowed charge value for the ions for that transition metal. Okay? So the idea here is that for transition metals, TM, the allowable charge value on their cations has a range or has options. Okay, and these are often experimentally determined or predicted from other properties of the metal and the architecture of the compound. Okay, so to show you an example of this, consider, for example, the cations expected for iron. Okay, so for iron, Fe, we see through experiment and analysis of other compounds that iron can be 1+, 2+, and sometimes even 3+ in charge. And so what we need to do is reflect the type of iron cation that we have in the name with an additional detail. We cannot simply use the rule that we have for the alkali metals and alkali earths, column 1, column 2. Those will always have a predictable charge value. Here, since we have many options, we need additional information. So what you'll see in the name for ionic compounds with transition metals is you will see a Roman numeral that speaks to the charge value of the cation in question. Okay? So let's take a look at a few examples. Perhaps we'll start with the compound name. So we could be given iron Roman numeral 1 oxide, and we could be asked to determine the formula. Okay. So I've included an ions domain in this chart to help us with our thoughts because we will need that. We'll also show the difference between that and iron Roman numeral 2 oxide, and this other option of iron Roman numeral 3 oxide, and show how the formula shows the differences there. Okay, so like we've done before, you would start by listing the ions that you know present. So here, clearly we've got ions of iron in all three of these cases. So these are going to be cations because we know iron is a metal, specifically a transition metal, likes to lose electrons, likes to form cations. We can't predict what the charge value is, so we turn to the Roman numeral to help us there. The Roman numeral to the right of the word iron tells us that this is a 1+ cation. Okay. The Roman numeral to the right of the iron in the word iron 2 oxide tells us this is an iron 2 cation. And likewise on that third option, Roman numeral 3, 3+ iron cation. We know from the oxide and the position of that anion in group 6 that the charge value has to be 2 minus, and that's going to be in common in all of these examples. And so with this information now we can list the formula for the compound. We can do our exercise of populating the subscripts to make sure that we are neutralizing the overall charge value. So clearly these are all going to be FeO ionic compounds in their formula, but the subscripts are going to distinguish them from one another. Okay, so in the first example, we will need 2 iron 1 plus to balance the 2 minus charge that we have on oxygen. For the next example, since there is a twofold charge on iron and that is matched in the negative direction by the 1 oxygen, we only need 1 of each. So actually the formula as listed, FeO, is complete and correct. In the next option, we see that we will need 2 iron 3 plus to balance the overall 6 minus that we get from having 3 oxides present. Okay, so our earlier ideas about predicting those values by kind of dropping these to the subscript positions to create the formula works, and there's no need for further simplification because 3 is a prime number. We can't divide it further. Okay, so that's how we've seen the Roman numerals in the word providing the additional detail to help us do an exercise like predict the formula or list the formula correctly. Okay, some additional options exist throughout other transition metals. So you'll see the same thing, for example, for copper. And so we could try doing a similar exercise for copper 1, copper 2, and copper 3. And in this case, we could be dealing with phosphide as well. Okay, so we'll list these entries here in the table, and this is an opportunity for you to pause the video and try your skills at completing the rightmost territory in the graph, that is completing the formula for these listed compounds by name based on what you know for the Roman numerals and what you know for the anion based on its position in the periodic table. So resume the video when you're ready. Okay, so we saw in this case what we deduced by the Roman numerals is that copper can be 1 plus, 2 plus, and 3 plus, and this is going to have impact on the subscripts in our formula ultimately. So copper 1 plus is what we have in the first case, 1 plus. Copper 2 plus is the next one. Copper 3 plus is the last example. We have to handle the phosphide now, so recall that's going to be phosphorus, not potassium. Sometimes those are confused. So this is in the 5th column of the periodic table. It's a nonmetal, so 5 minus 8 predicts a value there of 3 minus. So we're dealing with phosphide 3 minus in only as the option there. And now we can build our formula. So hopefully you predicted copper 3P1 for the first example, copper 3P2 for the next example, and finally copper CuP for the last example, noting that the subscripts could be simplified further to simply be a 1-to-1 ratio to ensure electron neutrality in that compound. Okay, so that's how we use additional details to reflect the options that we see for the transition metals. Unfortunately, there are a couple of exceptions that are known. The idea here is that we need the Roman numerals to reflect a demonstration in that there's several options for some charges in these transition metals. Now, silver only gives one known charge value. So the ion of silver is always silver 1 plus. It is always it gives up 1 electron from its neutral atomic state and only forms the silver 1 plus cation. no matter what you do. So we do not need Roman numerals for this one. Another example is zinc. The cation we get from zinc is always zinc 2+. There is no known examples of other zinc ions with different charge values. And the last option is cadmium. Okay. The cadmium Cd is always 2+. So for compounds with this, no Roman numerals are needed. That information would be redundant because we know that no other options exist. Okay. So there's an example there. So in a case like working backwards, let's say we were working with the formula first, zinc oxide. We can work our way backwards towards the name, knowing what the ions we're working with here. So hopefully the oxygen we see is a straightforward one. That's in column 6. That is always 2-. Given the formula being correct at simply ZN101, we know that the charge value on the zinc must match. So that must be 2+. Okay, so having that's an opportunity to check our work in that we've memorized zinc to be 2+ as well. And so anyway, we can figure out that charge knowing something about an ion that is more common, like oxygen. Okay, so now we can list the name finally. So working our way backwards. So this would be zinc. No Roman numeral is needed. Zinc oxide. And that is the complete and correct name. Including a Roman numeral is redundant. We do not need that. Okay. You could try another one here, like a nitride. So here's a nitride, and we can work with nickel nitride. Okay. And we will put this as the following formula. So Ni3N is the formula. And so work your way towards the left this time, completing this compound name, knowing some of these rules, and perhaps you can figure out the charge value on nickel without knowing anything more and only having the formula. Resume the video when you're ready. Okay, so we're dealing with a nitride, so that is a straightforward anion. That is in column 5. That likes to go to 3-, 5 - 8, 3. So that is a 3- anion that we are working with. Clearly, we're dealing with a transition metal, nickel. It is a metal. It wants to form a positively charged cation. Maybe we don't know the charge value, but we can figure it out from the formula. So the only charge value that makes sense here would be 1+ to reflect the 1 nitrogen that is included in this formula. Okay, we check our work. Nitrogen is not one of these exceptions, so we are going to be correct to list a Roman numeral. So we will list nickel. We need some additional details, so that is a nickel Roman numeral 1, nickel 1 nitride, to list the formula name there for that compound. Okay, takeaway is transition metals require a Roman numeral to reflect the charge value, since many options are usually available for the charge value on those cations from this D block of the periodic table. We have 3 exceptions that we must memorize: silver, zinc, and cadmium. Zinc and cadmium are in the same column. It makes sense that they might adopt the same charge value. Silver being the exception there, we see that right next door, and so that's at a lower value of only 1 plus instead. Perhaps that's a trick to help you memorize.